In this lecture, we're going to examine some of the some additional fundamental concepts related to the use of the ANOVA statistical procedure. And in using this procedure, there are some general assumptions about the data that are made when carrying out this approach here. The first assumption is that the data in question abides by the N01 rule, which is to say that the data have a normal distribution, so this points to the bell-shaped symmetrical curve that was addressed in earlier units, with a mean of 0. Centered around that is a standard deviation of 1.0. Now, in actual practice with real data, the data that violate this particular assumption will actually have very little effect on the computed F value, which is the test statistic, if this assumption is violated. And for that reason, the ANOVA procedure that was developed in terms of the mathematics is considered to be robust, which is to say that this is a mathematical approach that can withstand this particular violation to this assumption, of course, up to a certain point. The second assumption is that the groups that are being compared have comparable or similar measures of variability, termed the homogeneity of variance. And once again here, when we're dealing with real data, the ANOVA procedure is considered to be robust in that it can tolerate to a certain degree, differences in the standard deviation that are generated for each group. So it does not have a particularly large effect on the final test statistic, up to, of course, once again, up to a point. That point with respect to the homogeneity of variance is that the largest variance, suppose we have 3 groups that we are comparing. Recall that when we have 3 groups of data, the first step is we calculate the descriptive statistics for each group. Now, with respect to the variance measure, which is the standard deviation value squared, the largest variance should not exceed the smallest variance by more than 2 times. And if that is the case, then this violation to this ANOVA assumption may start to have an effect on the final F statistic, and other statistical approaches may be indicated. And the third assumption is that there's a complete independence of scores of each group or mean. And in theory, this aligns with the idea that the items within each group or within each set of data to produce a mean are randomly selected from a population or randomly assigned to different groups, conditions, and levels. And so there is no systematic or bias in putting one case in one particular group or the other. And the scores must be on a parametric scale. And these are are numerical values that are either interval or ratio data. So nominal scores or ordinal scores, which are certainly valid ways to capture variables of interest, one would not use the analysis of variance approach. There are what are called non-parametric statistical tests to deal with nominal and ordinal data. So overall, in terms of the assumption violations, this is particularly most sensitive when sample sizes, and I put in quotations here, are small. So researchers should aim to err on the side of a larger sample size, which does take more time to accumulate, but that does have the advantage in producing a more valid statistical outcome when those sample sizes are relatively larger. And to try to, as closely as possible, equate the sample sizes between groups. If the sample size difference between groups are negligible, that won't have as much of an effect on ANOVA as opposed to very significant differences, or very large differences rather, in the sample size between groups. Now, to understand the mathematics and the approach used in ANOVA, we go back to the concept of variance. And once again here, when we talk about ANOVA, we're talking about the analysis of variance. And so there are a number of variance measures obtained in this statistical approach. And before we move on to those sources of variance, we go back to recalling what variance is. And this all goes back to this idea of the concept of deviation, where X represents one person or one case in a group of data. And to understand deviation is to understand this idea of trying to figure out how much this one person is different than the overall group captured in the average of that group. And mathematically, we just subtract X, or we subtract the mean from each person's score. So once again, if we have 30 people in a particular group, we would have 30 different deviation scores. Now that led us to the problem of what's called zero sum. And so if we wish to calculate or get an estimate of how everybody deviated from the group average, we would end up with a value of 0, because approximately half of the people would be above average, the other half, approximately half, would be below average on the other side, and those would all cancel each other out. And so the way that was dealt with is that we would square each person's deviation score. So we still have one person, subtract the group average, that's one person's, that captures how much this one person deviates from the average, and if we square the value, all the negative signs go away. And so if this person's score is less than average, we would get a negative deviation score, but when we multiply the negative deviation score by itself, we end up with a positive value, and that's the square deviation. Once again, if we have 30 people in our sample, we have 30 deviation scores, and we have 30 squared deviations, and the next step would be to calculate what's called the sum of squares. We basically add up, summation symbol, all the squares. So we would actually perform mathematical addition over the 30 squared deviation scores that we have if our sample size is 30. We then divide the sum of squares by a concept called the degrees of freedom, which is n minus 1. And that will give us what is called sample variance. And recall that if we take s squared and take the square root of it, the square root symbol and the 2 cancel each other out, and that leaves us with the standard deviation. However, in the analysis of variance approach, we would not do that. We would calculate the sample variance and just leave it as such. That will be used in eventually calculating the final test statistic, or the F statistic. The ANOVA procedure is based, as the other statistical approaches, on a theoretical distribution of scores. And once again here, we take a look at the two main sources of variance that will go into the calculation of the F statistic. The first is what's called the between groups variance, so the variability in the average score between the different groups. That's the numerator. The within groups variance is within the groups, so the variability between the individual people within the different groups and how those individual people deviate from that individual group average, and that would be entered into the denominator. So what does this mean? If the F ratio is greater than 1.0, if it's greater than 1.0, that means the variability in the numerator exceeds that in the denominator. And so there's always going to be within variability. But if the within variability is very, very large, there's a lot of overlap between the different groups. However, if the variability between the groups is so large that it separates the distributions, then that would lead us towards a conclusion that would be statistically significant. What we see here on the bottom part of the slide is the theoretical F distribution. Now this is very different than the normal distribution and the T distribution that we observed before. Essentially, the F distribution is the T distribution squared. And recall that the T distribution is symmetrical about 0. If we square that, all the negatives become positive. But we take the same basic idea where we have the F ratio or the F value along the x-axis, so there are no negative F values here, and what we're looking for is separating the non-critical region from the critical region. And we're just eyeballing a spot right here, and we clearly see where the vast majority of cases are to the left of this red line. And everything to the right of this red line is what's called the critical region. And so in our study, if we calculate an F statistic that lands us in the critical region in this very long tail, then there must be something clearly unique about that comparison that separates it from the vast majority of cases to the left-hand side of this threshold that separates the non-critical region on the left and the critical region on the right. And so this lecture, we've concluded this portion of our lecture here on ANOVA that gives us this overall general theory about where the statistical procedure is going to go with respect to separating the critical region and the non-critical region around a very specific F numerical value that we call the F critical value that we will get from a table, much in the same way we did with the critical Z value and the critical T value.